Today's talk is going to be about the atom, the basic building block of all matter. So as you look around yourself, all the things that you see, and even some of the things that you can't see, are made of atoms. What we'll do today is we'll walk from the past, we'll take a look at some ideas about the atoms from a long time ago, to today, what today we now know about the structure and the behavior of atoms. Imagine you lived a long time ago, and you started wondering about what the things around you were made of. There was no electricity, there was no internet, there was no Encyclopedia Britannica. So it was just you and your brain trying to figure out what everything is made of. So a logical thing you might do is start taking things apart and seeing what's inside of them. And at the time, about 2,500 years ago, this is exactly what happened. A man named Democritus came up with the idea that everything was made of little tiny particles. He actually coined the term atomos, which is today's version of atom, which technically means no cut. Now, what he meant by that was that if you keep cutting things up into smaller and smaller pieces, taking them apart, eventually you're going to reach a piece that is so small it's going to be the smallest particle possible. So that was his idea of the atom. Now, that held for a little while, and generation after generation was born, and new ideas came to light, and new people of influence came to light as well, like Aristotle. Aristotle didn't really like Democritus' idea, so he said instead of just one little tiny thing, everything was made up of a possibility of four things. And those four things were earth, air, water, and fire. So everything around us would have a certain ratio of earth, a certain ratio of water, fire, and air all mixed together. So essentially, a Democritus idea gets swept aside, and earth, air, water, fire holds for a very long time. Now, what's interesting is that some years later, once all these people were long gone, the idea of the atom comes to today, and we now understand it, and it's very much like Democritus' idea that at the simplest level, we have this basic unit of all matter, this building block that we call an atom. So it was during that time, from 2,500 years ago till today, most of it was philosophical, but then they started doing more experiments. After the days of alchemy went by, people's experiments got better, equipment improved, they started discovering new elements and new procedures for doing these experiments, and two quantitative laws come about along the way. The first one is going to be this: the law of conservation of mass. If experiments are done well, what we find is that there's no detectable gain or loss of mass that occurs in a chemical reaction. Mass will be conserved. So like I said, if an experiment is done well, there should technically be no loss. What you start with should be the same amount that you finish with. Another law presents itself in the time from 2,500 years ago till today, after all these experiments and new discoveries are done. And that's the law of definite proportions. And it says, in a given chemical compound, the elements are always combined in the same proportions by mass. So what that means is, no matter where you get your samples from, if they qualify as a particular substance, they're going to have the exact same composition. Take water, for example. You could melt some glacial water, and what you should find out with melting glacial water is that you have 2 atoms of hydrogen for every atom of oxygen. Or you could say that oxygen makes up 88% of the compound and hydrogen makes up 12. Now, if you took some water from your local waterway and you did the same analysis to it, you should find out the exact same thing once it's been purified. You should have 88% oxygen, 12% hydrogen. You should have 2 atoms of hydrogen for every 1 atom of oxygen. That's what the law of definite proportions is all about. In the early 19th century, an English school teacher named John Dalton reasoned that if atoms really do exist, they must have certain properties to account for those 2 laws we just mentioned. He was able to come up with properties which we now know as Dalton's atomic theory. Let's go ahead and take a look. First, matter consists of definite particles called atoms. Absolutely. Number 2, atoms are indestructible. They cannot be created nor destroyed. So when we were looking at the law of conservation, that kind of seems to go with that whole principle there. Number 3, the atoms of one particular element are identical in mass and other properties. Number 4, In chemical reactions, the atoms rearrange, but they do not themselves break apart. And number 5, when atoms of different elements combine to form compounds, new and more complex particles form. However, in a given compound, the constituent atoms are always present in the same fixed numerical ratio. So, we talked about a couple of laws, the law of conservation of mass, the law of definite proportions. And this fifth part even leads the way towards another law called the law of multiple proportions, which we'll get to a little bit later in this class. But as you can see, we have 5 very strong statements about atoms. So my question to you is, are all 5 still valid today? Well, let's take a look at the next slide for a minute. Alright, well, we already see that Einstein is shaking his head no, and it says this theory is not perfectly correct. We now know that atoms can be broken into smaller pieces by way of what's called a nuclear reaction. So, what we know about nuclear reactions is we can go ahead and we can take matter, and certain types of atoms are unstable, and they will on their own break down. Now, sometimes we add a little persuasion to make those break down faster, but we also know that we can super collide atoms into each other and build them up. So nuclear reactions is going to kind of go against one of Dalton's 5 principles. The other one that's not valid today is the fact that most elements occur of mixtures of 2 or more isotopes. That is, atoms of an element have slightly different masses. And that goes against him saying that all atoms of a certain element are identical in mass and all the other things that go with it. But the idea here is that you can have multiple versions of the same element. For example, down here, whoops, sorry about that. Down here I have 2 peas in a pod. One of them has a pea pod that's green, one of them has a pea pod that's gray. Bottom line is there's still 2 peas in a pod, they just are slightly different from each other, which is the idea of an isotope. Alright, let's take a look at the structure of an atom. So the first 3 statements here allow us to go ahead and look at our model over here in the corner, try to make some sense out of it. So first we can see the yellow spheres represent, and from a previous grade there's no doubt that you've probably covered this, but if you haven't, the yellow spheres are called protons. The orange spheres are going to be found in what we call the nucleus with the protons, and those are what are called neutrons. The small white spheres that you see on the outside here, those are going to be electrons. So that's what we call our 3 subatomic particles. So when we say subatomic, we mean smaller than the atom. Well, those are the 3 particles that make up atoms. So protons, neutrons, and electrons. All right. So then what we can do is we can turn that into a nice concise statement here. The nucleus contains 2 things, protons and neutrons densely packed together. As you can see, it appears like they are in very close proximity with one another. The area outside the nucleus contains, and we've already mentioned, that is electrons. Protons have, and if you take a look right on their surface here, we have a plus, and that denotes to us that they do have a positive charge. And electrons have negative charge, which you can see on the electron itself, very small. Neutrons, however, they have no charge. They are considered neutral. So if you look on the neutron surface, it's bare, there's nothing there. Now, one thing that we need to consider as we look at this atom is that this atom is way, way out of proportion in a particular way. And that particular way is its nucleus. Right now, it's gigantic, okay? Nuclei are not this big. So if I could, go ahead and make the smallest dot possible with my little blue digital pen there, that's still way, way too large. Well, how large is the atom compared to the nucleus? Well, think of a sports stadium. And I want you to think of this as the outside of the atom. The nucleus would be about the size of a marble at the 50-yard line, right about there. So if you can imagine that, that's a lot of space between the nucleus and the electrons that surround that particular atom. Okay, another thing that's kind of out of proportion and not quite right in that picture is the fact that it seems like the electrons are spinning in a ring around the nucleus. Now, we know that is no longer the case either. Think of it more like a fuzzy ball, in the fact that you have a nucleus in the center, and out here you can see how this, you have a slightly diffuse picture here of a lot of dots. And these dots represent potential places that electrons may exist. We'll go more into that a little bit later. Here we have actually a bond. This is two atoms that are connected together, and their cloud of electron density is highest right here, and it gets lighter and more diffuse as you go to the outside. Here's another view. You can see that you have a positively charged nucleus in the center, and then it has a couple of dense rings here where in reality that is a mathematical probability of finding more electrons. So we tend to think that electrons now are found in clouds, and those clouds have very unique shapes, which we'll see in a little while. Okay, this is a table of atomic data, and this will be very useful to you as you try to understand what the atom is really like. So we have some categories here, what subatomic particle we're talking about, what the symbol is, the charge, the mass, and the mass relative to a proton. So let's go ahead and look at some of these columns. The first one, we'll say the electron, represented by the symbol E with a little negative superscript, has a charge of -1. Its mass is a very, very small number. As you can see, the 10 to the negative 28th power. That is extremely small. And its mass relative to a proton is very small too. It's about 1/1840th the size of one. So 1/2000th the size of a proton makes it a really small little particle. Second, the proton itself, symbolized by P+, charge is a +1. It's still really, really small, negative 24th power, which is bigger than the negative 28th, but still incredibly tiny. And its mass relative to itself would just be 1. And then lastly, the neutron, which has a symbol N with a little naught sign, a little 0 superscripted to the top, representing its charge of 0, equal in size and mass of the proton, and 1-to-1 ratio. So for a small little electron, it sure carries a pretty large equal and opposite charge to that of the proton. So for a little guy, it packs a lot of punch. As we start thinking about different kinds of atoms, we have to think about the periodic table because it categorizes them and organizes them in a particular way. So, for example, we have about 118 different elements here on planet Earth, and what we have is this organized system that uses these boxes here that we find on the periodic table to represent atomic information. For example, the number that we always find above an element symbol is called the atomic number. And that atomic number is sometimes referred to as the Z of a particular element, depending on the class that you have, but it is the number of electrons or the number of protons in an atom. Now, without a doubt, the number of protons guarantees identity of a particular atom from the periodic table. That is, if I have 2 protons in the nucleus, I have a helium atom. Electrons are usually that way as well. So if we have an atom of a particular element, not only the number of protons, but the number of electrons will also be that particular element as well. So if it has 2 protons, it has 2 electrons, and that is the nature of helium. Now, the reason why I was a little bit hesitant as I said that is because we're going to learn about an I word that exists in chemistry that tells us the number of electrons isn't always the best guarantee for determining identity. More on that a little bit later, but without a doubt, always prioritize number of protons first. Secondly, in any periodic table box, you're going to have a 1, 2, or 3 letter abbreviation, which represents the symbol, and often there will be the name underneath that symbol of the particular element. And these names can have multiple origins. They could be named after people, places where they were discovered, different languages. There's a variety of reasons why they are what they are. And underneath, what we typically find is some sort of number down here. Now, that number is called atomic mass. We'll get into this a little bit more later, but what it is, it's a weighted average of all the isotopes of a particular element. And I'm sure that sounds kind of complicated, so we will get there. But what we need to know is that atoms of an element have a certain number of protons and neutrons and electrons, and it's usually that proton and neutron number that's going to give a particular type of an element its weight. But we said earlier that you might have some elements where you have what's called an isotope, our first I word for this chapter, and you might have a little bit of difference in there, although it remains the same element. This slide's going to cover some fundamentals of atoms, and we'll do some vocabulary drops, so you'll be able to think more intelligently if you have these vocab words, as part of your everyday language while you study chemistry. And we'll start with the idea of a substance that cannot be broken down. And of course, that represents the word element, and we have 118 of them on the periodic table. All right. Second, the smallest particle of an element that exhibits all the characteristic properties of that element is what we call the atom. As we previously mentioned, atom contains 3 subatomic particles, so get used to hearing the term subatomic, and know that means smaller than an atom. Well, what's smaller than an atom? The pieces that make it up. We have protons, and there's the symbol for it, neutrons, and we have electrons. All right, next, the number of protons equals what's called the atomic number of that element. And you just saw it on that last slide with the periodic table box. Atomic number guarantees element identity. Also, all atoms are neutral. So if something is very succinctly called an atom, you need to know that it's neutral and your number of protons will equal the number of electrons. Could the atomic number also equal the number of electrons? Well, of course it could, if we're talking about an atom. Now, if we drift into the I word territory and we get into isotopes and ions, you got to be careful about that. For our first I word, we're going to go ahead and read this bulleted point. All atoms of a given element have the same number of protons and electrons. The number of something, though, may vary. And by process of elimination of those subatomic particles, I hope you're thinking neutrons. All right, when this does happen and your number of neutrons differs, you have our first I word called an isotope. All right, let's take a look at some examples of isotopes with this colored key up here. So the red dot represents protons, the green dot represents neutrons. And if we take a look at our first element up here, we see we have 1 dot for this H with a superscripted on the left side 1. We got 1 dot here and we got 1 dot there. What that tells me is because I have 1 proton, it guarantees my identity as hydrogen and nothing else. Now, if you notice the green dots, and in this case here we have 1, in this case here we have 2, in this one here we have none, that represents you have different types of hydrogen. They're all still hydrogen. We know that because they have a red dot representing 1 proton in their nucleus, but the number of neutrons may vary. So what that tells us is that we have 3 isotopes of hydrogen. There we go. Sorry about the messy writing there. 3 isotopes. All right. Helium, on the other hand, we know it's helium in both cases because, again, it has 2 red dots or 2 protons in the nucleus, but the number of neutrons varies. So in this case, helium has 2 isotopes. Okay? All right, in our third example down here, we have lithium with 3 protons. In both cases, 1, 2, 3 dots, 1, 2, 3. However, the number of neutrons varies. This one has 3 and this one has 4. So in the case of lithium, lithium also has 2 isotopes as well. Okay? All right. Now, the next term is going to be one that you really got to make sure you know what it is, because as you study the atom, you're going to have a lot of words and terms that sound similar. So flashcards work well. Repetition is the key here. This next one's called mass number, and it's nothing more than the number of protons plus the number of neutrons. And you find those in the nucleus. And that's going to be helpful in identifying the isotopes of a given element. So in the case of each one of these examples here, the number of protons plus neutrons. So in this one, it's just 1. There it is. In this one, 1, 2. There's 2. That's its mass number. 1, 2, 3 in this one. In this one here, it's 3 as well. 1, 2, 3. In this one, it's 4. So you'll notice that the number on the top left corresponds with that particular mass number. So in the case of this one here, this lithium example, 3 protons, 3 neutrons, has a mass number of 6. This one has a mass number of 7. So mass number is going to be something you're going to be asked to use quite a bit in terms of determining how many subatomic particles a given example has. Now, down here below, you see simple formula for calculating the number of neutrons if you know the mass number of that particular isotope. So, mass number minus atomic number gives you the number of neutrons. So, neutrons equals mass number minus atomic number. Okay, so let's figure that out. Let's start with this example right here. If I have a mass number of 7, which we already determined right there, protons plus neutrons, and we subtract the atomic number is number of protons, or red dots, 7 minus 3, and that gives me 4. So 4 neutrons would be the answer. For this isotope here of lithium, we have a mass number of 6. We subtract the 3 protons from it, 6 minus 3, and that gives me 3 neutrons. And we can do that with any example we're given, because we already know how many protons there are in its nucleus. We can look it up on the periodic table if we have to. So mass number minus atomic number gives us the number of neutrons. The last thing we'll mention about isotopes is the way that we name and write their symbols. So first, a standard naming type of procedure is just to say the element's name followed by the mass number with a hyphen in between. That's it. So here we have our first example of carbon 14 followed by carbon 35. Notice elements come first, then a hyphen, then a number, the mass number. So what I would then ask is how many neutrons are in each one of those. So let's go ahead and let's figure it out. Carbon 14. 14 is the mass number. Now, I thought we had to subtract atomic number from it. Where are we going to get that? Well, think about it. The periodic table. The periodic table has an atomic number for every element. And if you go find carbon, you're going to find out that it's 6. So 14 minus 6 is 8 neutrons. It's that easy. Chlorine 35. All right. So we have chlorine with a mass number of 35, and its atomic number from the periodic table is 17. So we'll just go ahead and subtract the two. 35 minus 17 is 18. 18 neutrons. Okay? It's that easy. All right, there's also something called a nuclear symbol as well. And these are even easier to use because they have the mass number over the atomic number followed by the element symbol. So this is what it looks like. And this, most of it's done for you. So if you have mass number minus atomic number and you were asked to find the number of neutrons, put a subtract sign there. 4 minus 2 is 2. This one has 2 neutrons. And that's often asked by a lot of teachers, how many neutrons come from a particular nuclear symbol. If we did a nuclear symbol for that chlorine example, we'd have 35 as the mass number over 17 Cl. And we would, again, just put a little minus sign in there and say, oh, it's 18 neutrons. It's that easy. And so the question is, how many neutrons were in that one? Of course, it was 2. 4 minus 2 is 2. And then lastly, it says, occasionally you'll get an element symbol with just a mass number. Why should you not freak out? So in the case of, like, let's say you got on one of your papers, you had to figure out carbon, and there was a 13 here as a mass number, but there was no atomic number. Well, you have a periodic table. You just look up carbon's atomic number. It's 6. So 13 minus 6 is 7. So this one would have 7 neutrons. Okay? So you shouldn't freak out. It's just as easy. Last thing I want to talk about today is the size of individual atoms. Now, of course, from our table of atomic values earlier, we saw those subatomic particles and how small they were. So the masses of them are extremely small. Some value times 10 to the negative third grams is pretty typical. The diameter, we could say that it's more in the picometer range, because remember that as small as the protons and electrons are, think of the marble in the stadium analogy, that it does go on for quite some distance if we can, get down to that kind of level. So 10 to the negative 12 meters is not uncommon. When they were developing the system of the small size of individual atoms and how are we going to base all the elements off of it, they chose a standard unit for everything else to be compared against, which wound up being the element carbon. So the actual mass of a carbon atom, as you can see there, is very small, 1.99 times 10 to the negative 23rd power. They chose the value of the carbon atom to be 12, what we call atomic mass units, or AMUs for short. So typically when you're looking through your book, you're going to see AMU as a unit. And it's a really small value. So 1 AMU then is going to be 1/12 the mass of a carbon-12 atom. And that kind of makes sense. So 1 AMU then scientifically would be 1.66 times 10 to the negative 24th grams, a very small value. All the other elements' masses are going to be relative to the mass of the value for the isotope carbon-12. And what we could finish this with is by saying the masses in the periodic table that are not perfect numbers, they're weighted averages of the masses of all its naturally occurring isotopes. So you saw with the hydrogen example, the helium example, the lithium example, hydrogen had 3 isotopes, helium-2, lithium-2. So which one do you pick for the periodic table? And the answer is you pick all of them and you average them together. So think about this, with hydrogen, there's 3 types of it here on planet Earth, and each one is a particular percent. And we got to crank through the numbers and do a weighted average of each element's percent abundances, is what we call it, to then get a value and put it on the periodic table. So we're going to explain that a little bit more in the future, but for now we'll wrap this up. What we talked about today is where the idea of the atom came from, what it's developed into today. We looked at the subatomic particles, and we talked about protons and neutrons and atomic number and mass number. We didn't get too much into the electrons, but let me just say the electrons are super important in chemistry because basically all chemical behavior comes from the number of electrons that are found on the outside of that nucleus. So a lot more to come. Keep reading that book, keep studying, and I'll talk to you next time. See ya.